Right, so in yesterday's segment, we looked at an introduction to a new design paradigm called backtracking. We saw that it is used in a specific type of problems which we call the state space search problems, where a problem is or a solution to a problem is represented by a bunch of states which progressively move from an initial state to an end state or an answer state. There are some valid states and invalid states depending upon constraints, and any algorithm which navigates through the state space to reach a solution is called a state space search algorithm. One such algorithm design technique we were looking at is called backtracking, and we saw that it is used for constraint satisfaction problems. We looked at a toy example where we had to decode a 3-digit password. So today we're going to be looking at another slightly involved example, which n queens, which is one of the classic examples taken in the context of backtracking, and we are going to look at the solution to this n queens problem by means of backtracking using the blueprint we saw yesterday. So if you remember the blueprint, it had 3 segments. One segment which checked whether a specific state was valid or not, one segment which generated all the candidate states, and one segment which did the actual backtracking. So we are going to look at the Python code for the solution to the n queens problem, and that code, as you will see, is divided into these 3 segments. So before we look at the code, we'll start by understanding what the question says. So the problem is called n queens, and the statement is as follows: given an n cross n chessboard, place one queen on each row and each column, that is overall n queens, such that no queen can attack the other. So if you are familiar with the chess game, which has multiple pieces, king, queen, bishop, rook and knight and so on, you might be aware that the queen is a piece which can move vertically, horizontally and diagonally to any number of steps. So if you place a queen on a specific cell in the chessboard, any piece which lies in the same row, same column or along the same diagonal, left diagonal, right diagonal, can be attacked by the queen. So our objective here is, given an n cross n board, you have to place n queens, hence the problem name, one on each row and each column, such that no queen can attack another queen. So that is the problem statement. This problem is defined for sizes 4 and above, meaning the board should at least be 4 cross 4, because obviously if it's a 1 cross 1 grid, there's only one cell, you only have to put one queen, so you'll put it on that cell obviously. And for 2 cross 2 and 3 cross 3 boards, it is not possible to place as many queens such that no to attack each other, because if you take a 2 cross 2 board, every cell is adjacent to every other cell, so no matter where you place 2 queens, they're always going to be able to attack each other. Similarly, you can find out that it's not possible in a 3 cross 3 case either. So generally the n queens problem is defined for any chessboard of size 4 cross 4 and above, and there may be multiple valid positioning of queens for any n cross n board. So if you take a 4 cross 4 chessboard, which is the example we will be looking at in today's segment, you'll see that there are 2 valid solutions. So there are 2 different ways of arranging the queens such that all our constraints are satisfied. So it's not necessary that you should have only one solution for a given value of n. And so obviously when you have multiple solutions and you want to find all valid solutions, we'll go with backtracking. So that is the problem statement.